Welcome to this Tutoring Center video. You can follow us on social media if you'd like to. I will be presenting today. Today we are going to solve a discrete time convolution problem. Let's solve this discrete time convolution problem. The first step in a convolution problem is to do a change of variable. The reason we do this is because we need two variables, one for the time index and one for the summation variable. By convention, we use k as the summation variable and n for the time index. So, we will change x of n and h of n into x of k and h of k. Their graphs still look exactly the same as before. We are just changing the variable from an n to a k. The second step is to pick one signal and flip it across the vertical axis. We can pick either one. We will get the same answer either way. I am going to flip x of k. The third step is to take the flipped signal and slide it across the other signal. That is what convolution is, visually speaking. We slide one signal across the other and see what comes out. That is what the n variable is representing, how far x of minus k is slid across. In this picture here, n equals 0, because the original x of minus k is not shifted at all. Sometimes, when doing discrete time convolution problems, it is better just to solve it visually and not use the formula at all. I think this is one of those problems. So let's start solving the problem now, which is to find y of n. As I said before, this image here is showing when n equals 0. By looking at this picture, we can determine what y of n is at n equals 0. In fact, we can determine y of n for n less than or equal to 0. We find y of n by looking for overlap between the two signals, h of k and x of n minus k. For everywhere there is overlap, we multiply the two signals together and add together all such products. Since there is no overlap here, we know that y of n equals 0 for n equals 0. And if n were less than 0, meaning negative, then x of n minus k would shift to the left, where there would be no overlap. Therefore, we know that y of n equals 0 for n less than or equal to 0. Now let's look at the graphs for when n equals 1. As you can see, x of n minus k is shifted to the right by 1, since n equals 1. Now we do have some overlap. The impulses overlapping both have a magnitude of 1, so y of n at n equals 1 is 1 times 1, which is 1. Now let's take n equals 2. We see x of n minus k is shifted to the right by 2, since n equals 2, and we once again have overlap in one spot. So y of n for n equals 2 is 1 times 1, which is 1. Now take n equals 3. We shift x of n minus k to the right by 3 this time, and now we have two places where there is overlap, at k equals 1 and at k equals 3. We multiply the signals together where there is overlap and add up the products, giving us 1 times 1 plus 1 times 1, which is 2. So y of n for n equals 3 is 2. Lastly, we take n equals 4. This is the last one because the overlap will be the same for all greater values of n. Remember, h of k, the red graph, goes on for forever, even though I cut it off at k equals 4. So if you were to slide x of n minus k further to the right, it will always have the same overlap, being all of it overlapping with h of k. We can see that all of x of n minus k is overlapping with h of k. Therefore, y of n at n equals 4 is going to be 4 times 1 plus 1 times 1 plus 1 times 1, which is 6. And again, y of n will also be 6 for any n greater than 4. We now have all the values of y of n that we need to express our final answer. You can express y of n as a piecewise discrete function shown here. You can also draw the graph. Remember, the graph goes on forever. What is shown is just a piece of the graph.